All right, welcome back to another lab application. In this lab application, we're going to try to attack this problem in which the light is coming from this 3.5 refractive index waveguide surrounded by these claddings of 3.498, and it's trying to penetrate into this narrower waveguide with 18 micrometers with 1 micrometer cropped from each side, and at the end it's going back to that 20 micrometer again. So this is the z equals 0 portion, and I mean in terms of the coordinates, and the whole perturbation takes place from -a to +a. All right, so we're going to use a MATLAB program to analyze this. This whole thing is taking place at a wavelength of 1.3 micrometers. As the first step that I have written for you here, we need to come up with the modes, the eigenmodes of the unperturbed modes. So let's look at our MATLAB code together. I'll just drag this to here. All right, so now I think you can see the MATLAB code. So it just starts like the usual deal. We need to specifically show the refractive indices that we are working with, the operational wavelength, the unperturbed slab thickness, and it's just going like that till this part. It just warns us that we need to choose our the modes appropriately. So I'll show you what I mean by that in a few seconds. And then as this problem is trying to determine, we need to get a coupling from a mode to the other one. In this case, we're going to try to investigate the coupling from the 0th order for the TE modes to the 2nd order for the TE modes. All right, so let's start, and can go back to this code again. All right, so I don't know how my connection will go with the server. So let's hit the run here. Okay, so it's something very familiar that we've already done is just prompted. And what we're going to do is we have to determine the two modes that we're interested in, the 0th order and the 2nd order, as I told you. Why not the first 0th order and the 1st order? Well, the 0th order is an even mode, and the 1st order or the 3rd order, they're odd modes. We cannot excite an odd mode by using an even mode like the 0th order. So the only order we can excite, and the math will also confirm what I'm saying, is going to be the 0th order to the 2nd order. So let's zoom in and try to find the KZ as usual. All right, so this is like around 1.35 e to the 5. All right, and the other one is gonna be below actually. So what you can do is basically, it's gonna take a little while, but since we can't see the intersection point here, you can come to this minus y position. Okay, so now it's more visible. So let's look at that. All right, so this is the point we're interested in. So it's somewhere in between 3.9 and 4. 3.95 would be a good estimation. All right, so let's go back to this window, the main window, and actually we can let's just remind us, this is going to be like 1.35. It's going to be like 3.95 times e to the 5. Okay, 1.35 e to the 5. So that's the first one. And the second one, as I told you, it's going to be, we're just going to estimate it to be initially around this. And yeah, so this has done the same things that we did before, found the eigenmodes. All right, So where are the eigenmodes? Eigenmodes are here. So as you can see, they're both nice even modes. That's the first mode here, this zeroth mode, I'm sorry. And this is the TE2 mode, the second mode. We're trying to couple from the zeroth mode to the second mode. So after seeing this, let's go back first to the PowerPoint and explain a couple of things there, and we can come back to the result again. So we have these possible options, and I just written down and made a small table showing all the propagation constants for these different modes, and also the normalization constant. As you might remember, we have to normalize these modes, and what we're assuming is that we have 1 watt in 1 centimeter per centimeter. So 1 watt per centimeter, that would be our normalization for the input power. And for that, we have these modes appearing. And as you can see, only the even modes are the blue one and the cyan colored or turquoise colored one. All right, so let's go one step further. And what we're trying to do is we're trying to understand as TE0, the zeroth order TE mode, how much that would perturb the second mode, TE2. Okay, so that's why on the left-hand side we have TE2. And for that, we have 2 regions, as you know, from 0 to minus L over 20, and from minus L to minus 19L over 20. So, but they are both identical. So if you calculate one of them, you just need to multiply it by 2 to get the total result. And that will have this coupling coefficient, let's call it capital kappa, 0, 2, from the 0 to the second order. Okay, and then we calculate that to be this much in terms of centimeters. So be careful, we converted that into centimeters. So let's just drag this here, and you know, it's very useful to use this workplace thing here for the MATLAB. So if you come here, you find that, yeah, this is the coupling coefficient I was talking about. So that's the coupling coefficient from the 0th mode to the second order. All right, so let's go back to the presentation once again. So that's that number, but that's not good enough, because while doing this, right, we're assuming that since we're taking TE0 outside of the integral, I'm sorry, not here, but it's going to be, we're assuming TE0 amplitude to be constant, all right? So, and that will be important for us in the coupling. And if we just try to understand how much of that TE0 would be perturbed by its own TE0 mode, okay? So that's why I'm replacing the second order with the 0 mode here. And I'm trying to understand the coupling coefficient for its own, the K00. All right. And that turns out to be smaller than the 0 to second. And if you look at the whole governing equation, we see this again for the 0 mode, and the negatively going term cancel out because it has this phase that is rapidly changing. So if you integrate it, it won't really matter. This, on the other hand, has the same phase with this one, so these two will be important. And if we look at this, it will just boil down to this simple equation, and that will tell us that the TE0 will be determined by this along the propagation direction x, okay? And up to 0.1 centimeters, it changes very little. So we can really assume that TE0's amplitude is not changing at all, almost not changing at all. So actually we can really arrive at this with our, I mean, just after calculating this one here. All right, so you can come up with the same kind of a plot yourself by just plotting it with respect to the propagation. So if I want to do that here very quickly, plot, I think it was X was the, yeah. So we're trying to plot X versus exponential minus J times coupling from 0 to 0. This is in terms of centimeters again, so you have to be careful, as I told you. And the other one will be the X again. So the X also needs to be in centimeters, okay? And it's shown to be centimeters too. All right. So let's put another figure comment here so that the background figure will not be destroyed. We need another parenthesis there. Okay. Yeah. So it's the same plot that was shown on the PowerPoint slide. So as you can see, even if we propagate for 0.1 centimeters, the amplitude is actually, the real part of the amplitude is changing only a little. All right. Let's go back to the PowerPoint again. So I think it was given together on the other plot. So let's go back to the main equation again. After finding out that a amplitude of 0th mode changes very little, let's multiply each side by this to understand the coupling to the second order. So we can arrive at this phase term here for the TE2 minus propagation, backward propagation mode. And again, that will be a very rapidly changing term, so that will destroy this term here. We're going to be left with only this term. Yeah. But in this case, this is going to be a small changing phase term because there's a minus negative sign in between the two phase velocities. And we will have to solve for this, of course. In order to solve for this, and you will now understand why it's important to assume that TE0 is not changing with X. If you look at it, we have to take a small integral with respect to X, as you can see. But to do that, we need to come to our initial assumption and say that, okay, this is not changing too much. And if we do that small integration, we come up with this general equation. If we look at the boundaries from minus a to plus a, and if we think about it, we didn't have any second order mode initially at minus a point. So if you put that into your equation too, you immediately arrive at the a TE2 mode at point A, and that's going to be given as less. For any x value, actually, it's going to be just replace A with x there. And if we just square this term, you will end up with the power. So that will start, yeah. So that will change, that will show us the power change along the perturbed zone. So as you can see, along the perturbed zone, the coupling from the 0 to the second order is like this much, like a little bit higher than 3.5%, which is not too big, but still there. And if we look at our other assumption, as we said, the change in TE0, the zeroth mode itself, is very tiny. And at the peak point, it's really like smaller than a change lower than 0.5%. So that's really much lower than that, actually. So that's really a good assumption then. Okay, so we now know the results of our discussion. we know that the second order mode will be excited by the by the zeroth order mode, because they're both even. And how much would it be excited? Well, at max it would be excited by this much, slightly higher than 3.5. And during this whole thing, even if we propagate by 0.1 centimeters, we will still have a change less than 1% for the zeroth order mode amplitude itself. So we can safely do our assumptions rigorously here. And the other thing that we need to be careful about is that this is like a sinusoidal change, as we can see from here. And so that's like a periodically coupling and decoupling. The second order mode gets the power by getting excited from the zeroth order mode, and then returns that power back to the zero order mode here again. But of course, we are ignoring that returning power to keep the for our assumptions. But that's not a that's already what we initially start with. So there's like a power change between the zeroth and the second order, as we can see here. Yep. So we covered everything that was important here for our sake, and I hope to see you in the next lab application.